6, a helping hand with your land.
Hey guys, Neil from Essex here. New Holland Agriculture is one of our primary product lines, and we're really fortunate to be located really close to their corporate headquarters in New Holland, Pennsylvania. They're located just about 30 to 40 minutes away from us, depending how bad traffic is going down that direction. New Holland has a legit manufacturing facility down there that has periodic public tours available, and it is a fantastic public tour to do. A lot of times when you do those kinds of factory tours, they're very controlled, right behind glass or behind the painted lines on the floor. The New Holland factory tour is fantastic. It is a real factory tour. It's a place where steel is cut and parts are painted and things are put together. It is a legit factory, not one of these funny assembly plants. So today's video is going to be the first in the series of us going through on this factory tour. The entire thing with the plant manager took us about 3.5 hours to go through. There's a lot of great content, and the plant manager himself is fantastic to listen to. So join me here today. We're going to start in this series taking you through the parts production portion of the factory in New Holland, Pennsylvania. Neil from Essex here with Tim Smith, the plant manager of the New Holland factory here in New Holland, Pennsylvania. Tim, what are you going to show us here today?
Yeah, we're going to take you out. We'll show you our hay tools plant here in New Holland, Pennsylvania. We're going to show you round bales being made. We'll show you disc lines. We'll show you some square bales being made, and then some other minor hay tools also all made in the same factory. So it's a privilege to show you, from parts making right through to the finished product.
So come with us here today. We'll give you a quick tour.
So this is a blank, this is laser cut blank. Okay, this is for a disc mold conditioner header beam weld assembly. And what you see here is the laser blank comes in from the lasers, and then the robot will pick it up, and it's doing what is sort of a forming operation. Now this forming operation historically is done on a press brake. You can imagine with 2 operators on either end. They're bending the part as the machine, they're lifting over shoulder as the machine forms the part. So what the robot allows us to do, number one, is it's unmanned. And then number 2, it eliminates that human error or that human injury possibility of over shoulder lifting. Cool. So from a cost standpoint, we've gone from really what would be 2 men for 2 operations, so 4-man operation, down to we probably cost this at sort of a half-man operation. We have a machine minder that watches over the robot.
So how does the robot know where the skid of parts is at on the floor?
Right, good question. So let's watch it. It's at the end of cycle. It's going to put this part now over on the finished skid over here. Okay, so if you look at that, it's pretty neat the way it nests them. It's putting one up, one down, one up, one down. It's nesting it, right? Now it's going to go back to the blank, and the first thing it's going to do is take a photograph of the blanks. If you watch, it's got a camera. It's going to flash and take a photograph. So there it's looking to see the orientation of the part.
Find the edges.
Yep, takes 2 pictures, figures out where it is, and then begins the cycle again. So you can see our operators stack that pretty good. They use the holes to put a driving pin in there and line it. Okay. But even if that moved slightly in, let's say, transition or in when it was being driven here by a fork truck, the camera can adjust and it blanks being out of line. Yeah, awesome. So, pretty neat investment. This is our first robotic press brake that we installed in this plant. This is a Trumpf model. We put this in, I want to say, 9 years ago. You can see it's doing a hemming operation. That's pretty unique. See that tooling right there? It's doing a hemming operation. That's pretty unique.
So the part that we're looking at here, you were just telling me this is a combine part. You guys don't build combines at this facility, so this is headed out to Grand Island then?
It goes out to Grand Island, Nebraska, where they make the combines. And so what this is, it's the rotor cage, the 2 halves that make the rotor cage. And so it's abrasive resistant material, of course, because of the wear that takes place inside of the cage itself. So it's abrasive resistant material. We laser cut it on our lasers. And then it comes up into this preform operation where what the guys are doing is they're putting in 2 preform 90-degree bends. They're doing it on a 600-ton Cincinnati press. And it's what we call bottom feeding. So like what we saw on the robot over here was precision forming or air forming. Here the die bottoms out. And so it actually punches right through there. It's a solid fix, hits the bottom of the die. The punch of the die actually, squeeze the metal, where on an air form, it bends, to a precision point. So the reason you need to do that is because of the geometry of the form and also because of the resistance of the material. It's very, abrasive resistant material. After they've done this preform, then they'll put in the big radius. They'll bump it around and do the big radius, and they'll get the finished component, which you can see over here.
So that's a 1/2-inch sheet. How do they get that in there?
So yeah, so we'll go around the front of the laser and we'll see the FMS system, or the handling system, where we put the material in a tower, and then there's 2 beds here. So this is, right now it's cutting 1/2-inch steel, and what we're cutting out here, you can see on the TV screen, is the sledge arms that go inside the round baler. It's a 4-foot sledge arm, 2 of those per round baler. And this is a 5,000 watt laser. It's what's called a, our other lasers are flying optics, which means this is a flying optics machine, which means that the bed never moves. You can see the sheet of steel never moves. So the laser head moves in the X and the Y direction, and the steel never moves, right?
Huh.
So what that means is when it's all finished, then this bed will roll out, and there's another bed underneath that will roll in. That's the only movement that happens on the bed. So what it allows the laser to do is to move fast in the X and the Y direction, and the sheet steel stays still.
When you look at, say, something like a round baler, I think a lot of our customers would have the perception that there's a lot of supplier parts in a round baler. I mean, you guys are really...
we're very vertically integrated.
Yes.
So I mean, to give you an idea in terms of part count, as a plant, so as a plant level, we buy 6,000 part numbers and we make 16,000.
Okay.
So that's at a plant level.
Yeah.
Some of those 6,000 part numbers include hardware. So nuts and bolts, we're going to buy them, right? But in a round baler, the make percentage is, I think, upwards over 65%. Okay, so it's pretty high.
Yeah.
Some of the rubber components, we, of course, would buy those,
That's one of the things that's always really impressed me about you guys down here. This is not an assembly plant.
Right, no,
right?
We're vertically integrated.
It's
raw metal coming in the back like this, right? So we see sheet metal here. We're cutting out sledge arms. I showed you side sheets being cut out. We're seeing them being formed. We go machining. We'll see induction. We see heat treat. Very vertically integrated. The components we buy typically are low-level components like nuts and bolts, and then things we don't do like rubber, or plastic. What the screen shows you is a visual of the nest. So you can see here, this is where the laser is right now, moving up. What's in green is already cut. What's in gray is what he's going to cut. And you can see the way the software works. It nests the component. You see how steel is not cheap. As you nest them up like this, you can see that we are trying to use as much steel as possible. And you can see here how the computer software has squeezed those together. I'll show you some other nests where we may take another component and slot them in spaces like this and try to cut that up.
Is it typical for a sheet to be one part, or do you often mix parts?
It's totally dynamic. So the software logic will say, of all the components I need to make today that need to be made out of this steel, I squeeze them all in. Now I know that this steel, this code of metal that we're using for this component is very limited in terms of the part numbers. It's a 1/2-inch material. It's very strong metal. It's part of the sledge. There's a lot of tension in the sledge when you imagine the round belt, the variable belts on there, making a bale is incredible tension. So these arms are very strong, and it's 1/2-inch material. We don't make a lot of components out of that. So if I go to a more common 1/4-inch code, you'll see multiple parts made out of the same material.
So when you say you might mix parts, I mean that layout on that sheet is dynamic.
Totally dynamic. I'll show you examples of that. Yep. What we're cutting here, this is the abrasive resistant material making the rotor cage that goes to Nebraska. Here we're cutting out the cage, and then later on it gets a forming operation, which we see on the press brake. The interesting thing about this pattern is there's so many holes. You can see how many holes there are in the cage. With laser technology, it's not the cutting that takes the time, it's the piercing that takes the time, okay? What this machine is called a Trump, it's a CO2 laser, it's a Trump 5,000 watt machine. We've had it for about 4 to 5 years. Prior to this, the technology used what was called, it would stay in a spot and it would peck away at a hole and pierce a hole, which means that it would take about 6 seconds to pierce a hole. On this machine, you can't even count how, that's less than a second pierce time.
Right.
So this technology, in the matter of 10 years, has gone from 6-7 second pierce time to, 1/2 a second pierce time. It just, boom, blows through in an instant. So
when I would think of lasers, I'd think, okay, laser cuts metal, but there's variations in types of lasers depending on the material that you're cutting.
The material you're cutting, I mean, this technology you're looking at here is called a CO2 laser.
Right.
Right? So you're taking 3 gases. You can see the electrical beam here. So these are the 3 gases that are in sort of that lightsaber look, right? That's 3 gases all being sent together, then they get charged with 5,000 watts of electricity. Then it gets refracted through lenses to make a very fine cutting point. The latest technology in lasers is what's called fiber optics, where you don't even cut with gas, you're cutting with light. So one of our sister plants in Nebraska, they've just installed the first fiber optics laser, and something that we would move to next is to say...
So when you say CO2, is CO2 the laser itself, or is there actually CO2 in the...
No, the CO2 is the gas, so it's a mix, 3 gases mixed together. It's nitrogen, carbon dioxide, and hydrogen. All 3 gases are supplied in a chamber, and then they're charged with electricity to make essentially a big beam. And then that beam is then refracted through to a very fine point through light through lenses.
So we were just talking about how parts are nested on a laser. So this is what, the layout of what the nest looks like?
Yeah, so this is a more common material, right? So this is a 1/2-inch material, or actually might be 1/88. And so here you can see the round baler side sheet component that was made up on a nest, and then you can see how that we've squeezed in these other components, you know, to use up the metal.
And you were saying that part sheet is dynamically generated.
Dynamically generated. So we don't have engineers sitting in the office doing this. The software does it out on the shop floor. The operators create a nest, and the software then will insert as many parts as it can into that material to utilize as much steel as possible. This is an older machine. This is what we call a hybrid machine. So the other one we saw was a flying optics where the bed was stationary. This one you can see the bed will move in the in and out direction, in the X direction, and in the Y direction the head will move left and right. So the head just goes left and right and the bed will go in and out. The advantage of that is the physical size of the machine is smaller, and you can put, you know, like in this case we've got 4 machines in one cell.
Right.
What we're cutting here, you can see long slats, you know, that these are basically probably going to make, I believe these are going to make, on the pickup, the bands on the pickup,
okay.
Yep, pickup bands. And then you can see an example of where we've nested some other parts in on the end to use the utilization. So a lot slower, you can see it's a lot slower when we nest 4 machines together, right?
So there are 4 running here.
4 running, 1 operator runs all 4. And then if you look at this machine over here, I mean, if you look at that, you can see that that nest is very well utilized. There's not much steel on that sheet of metal that is not product.
Right.
Yeah?
Yeah.
Then the sheet that's not, like the holes and stuff like that, they drop out. You can see they go in the bottom there. Yep. Then we sell that back. It gets melted down and makes recycle and comes back to us as a lower grade recycled material. Okay. It goes into some cheaper components. Yeah. We want 100% recycle as a plant, 100%. Yeah, so there's an example of what that machine is cutting. That's the nest. You know, you can see we're making this part number 1 and part number 2. It's a very simple nest. In this case, 2 part numbers, but you see it's using, you know, over 95% of that sheet of metal. All the scrap in between, you'll have a skeleton on the outside, and then the holes will drop out, and then we will melt that back into a lower grade steel. So very good example of efficiency here of using steel.
So do these run 24/7? They run depending on shifts?
So depending on shifts, I mean, when we were really heavy, you know, on volume, we would run what's called a continental shift, which meant we ran, you know, 4 days of 2 12-hour shifts, and then we ran a weekend shift, so we were 7/24. Okay. Nowadays, as you know, the hay market's down, so we're running less. We're running basically 1st and 3rd shift, Monday through Friday.
Still, that's still running.
Yeah, still good volume. Yep. Yeah. We also support.
The machine doesn't sit.
The machine doesn't sit, right? And we also support the combine plant, which is Grand Island. We also support, you know, the plant in Saskatoon. We make some components for them as well, which is Canada. So we've got some sister plant components that we make here as well.
So that's loaded with all different types of steel.
Yeah, we'll put. We got 10 trays. We'll load 10 different types of material in there. Sometimes the same, but it could be, you know, 10 different types. What you're going to see here is a material change out. So it's going to come down, pick up some material, and put it on an empty bed. and that will wait then to go inside the laser. So all this is internal to the laser cutting time. So while the laser's cutting, it's pre-staging the next nest or next material that it needs for the laser.
It's pretty much everything you guys make is usually steel. You're not using aluminum or anything else?
No, very little. I mean, there are a few aluminum parts, but it's
mostly steel.
Yeah, mostly steel, yeah. What I'm going to show you is Barry's doing what's called precision forming. Okay, so if you notice the die does not bottom out with the punch, right? Yeah. So you know, this is a 4 or 5 hit part. You can see there. He's got a 3D image on his screen, so everything's programmed 3D to show him where his next bend goes and what the part should look like. And then he's also got, you know, the print here, you know, that he can look at the details as needed, right? So some good examples of, you know, forming technology has been around for a very long time.
Right.
Precision form has been around for a very long time. Some of the unique things that we got here is that we never change those dies with punches. They're always set to the same radius and the same opening. And we direct the work here. You can see he's got 2 sets of tools, whether he's running on this or this. They've got different diameters and different size. And but what's unique is, I mean, or somewhat unique in the last, let's call it 4 years, we 3D program everything offline, so you can visually see the part before you form it. And the idea of the prints, you know, coming in sort of a bit like an iPhone, you know, I can zoom in instead of having a paper print. I can sort of move around, inspect the part, you know, so everything's paperless. We've done paperless
in terms of being an experienced operator, I mean, he's not just running that to the bottom every time.
No.
So is there, would that be a fairly skilled position in knowing where to stop and how to...
Absolutely. This is what we call a grade, like a grade 6 press brake operator. Barry's been with us, you know, been with us for I think 20-something years. You know, very fortunate, high skill. Barry can set up his own parts, program his own parts. When we develop new parts, he'll develop those programs. Nowadays, we do them offline, and so that gives us the 3D image, right? So we can program outside of production time. So we can have somebody in the office doing that. Having said that, if we had the program of the machine, Barry could do that, right? We'll send the program, he'll dial it in, and get us our finished part. This type of machine runs, on any given week, it could run somewhere between 80 to 90 unique different part numbers.
Wow. So. And would you be changing tooling and stuff all
Never
the time
change
to do
tooling.
that?
Never change tooling. Always keep those tooling the same. Never take it in or out.
Wow.
We direct through planning. The software directs all the parts to this machine that require that punch or that die or that punch or that die. You never have to take the tooling out.
Oh, you say software directed, so kind of like the planning on what goes on the sheets.
Right.
The same thing is happening.
So we take all our parts, we group them into families based on radius and length, and based on their bend length and radius, we'll direct them to what machine they need to go to.
Oh, that's fascinating. So we were looking earlier about the parts being cut out, and this is the sledge frame arm right there, right?
That's a sledge frame. We saw that being cut on the laser. So, you know, what you're seeing here is a 19-year-old Mazak that we've done a complete restoration on this robot. And so what happens on this cell is we make the full sledge arm. So you see the arms come in that were made being cut over on the laser. We buy that tube, we marry them together, and then they get robotically welded in this cell.
A piece like that could be easily human welded too.
It could be human welded. You got better quality with robotic welding. You're doing a 360 weld around the tube. So obviously human, you know, that's difficult ergonomics for a human. So the robot would tend to do that better, right? And then you can see this is the finished serpentine that gets pushed over into the assembly line. Okay. I think the unique thing here at this plant is we don't have welding, you know, and then as a separate department. Welding is feeding directly into the line. Right. You can see that this weldment, there's what, 4 frames there. They're going to go over into the assembly line. If there's any quality issues, we know about it right away. So it's single piece flow feeding directly into the line. They come right across. You can see they get pre-primed, get some paint put on because they're going to marry on 2 metal surfaces, and then they get dropped inside the frame.
Thank you, Tim, for walking us around today. That was absolutely fascinating.
Great.
Really appreciate the quality and the care that you guys put into this stuff. It is absolutely wonderful. So I appreciate you showing that to us.
Thanks very much, and we're very proud of our safety record too. We're glad you made it through the tour and there was no accidents. Thanks very much.
Thank you.